Hello and welcome to another video. In this video, we're going to be doing minimum time to revert word to initial state 2 and 1 from weekly contest 383. The intro is going to be the same, and then there's going to be optimizations we need to make it past the hard constraint instead of the medium. So let's go read it over. So we have a 0 index string word, integer k. At every second, you must perform the following operations. Remove the first k characters of word. Add any k characters to the end of the word. They don't have to be the same ones you removed, but you have to add something, and you have to do this every second. Return the minimum time greater than 0 required for a word to revert to its initial state. So you have to do this at least one time. So let's look at example 1. We have ABA, CABA, and they tell us after the first second, we can remove ABA, and we can add BAC to get this. Then after the second, we can remove CAB and add ABA to get the word we had. So this is 2. In example 2, it's 4 operations, and they go through like pretty much what happened. Or sorry, it's actually only 1 operation. You can remove ABA, and you can put, you can remove ABAC, and you can put CABA. So then we will get ABA, CABA, which is the exact same thing. So this is 1 operation. And in the third one, at every second, you'll remove the first 2 characters of words and add the same characters to the end of the word. After 4 seconds, the word becomes equal. So you would just remove and put things back. Okay, so let's kind of walk through that example. Or actually, instead of doing that, let's walk through this example. So let's walk through this example. Let's say k equals 4. And let's kind of see what's going on and what we're doing and how many operations. So in 1 operation, we have to take the first 4 characters and we have to remove them, and then we have to add them to the back. So we'll put it over here, and we still have this array here. So, and let's actually move this over here so it's lined up. Okay. So if we can make these 4 characters, these are the 4 that we moved, right? And we can actually have it even separated out a bit. So let's do that. So let's try to move it over here like this. So these are separated out. These can be anything we want. Can we make these 2 strings equal? No, we can't, right? Because this part, it doesn't equal this part. So let's do that again. So let's take these characters, 4 again, and let's move them to the end. Now, can we make this equal? No, we can't, because ij is never a and b. And if we do it one more time, so let's actually move this all over here. So now we take 4 again, which are going to be these 4, and we move them at the end again. So now notice that we've basically moved every single character here, right? We've moved every single character, some characters multiple times, and we can make them whatever we want. So any one of these characters can be whatever we want. So we can just figure out like, what did we need to make these to make this word line up? And that's kind of the idea, is whenever you move a character, you can make it whatever you want. So if a word is 10 characters and k moves 4 at a time, once we've moved every character, and like what's the math there? So it's just going to be the length of the word, right? So 10 divided by 4, and it's going to be a ceiling divide. So we'll get 3 here. So in 3 operations, we will have moved every single character, and then it's for sure guaranteed that we were able to make these words match now. So that's kind of the idea, is once you actually move every character, then you just have to figure out like, well, what did I have to change it to make it line up? Because if you moved every character, you can make every character whatever you want. So if you have 2 words, and in one of them, you can make every character whatever you want, obviously you're going to be able to make them equal. But there's going to be cases where you're going to be able to do this faster, right? Because here we can make it whatever we want, but it might actually be faster. For example, let's say our whole word is A's. Then after 1 movement, the characters are equal. So let's go through another example like this. So let's get rid of these things though. And let's go through another example with using example 3. So we're going to be using this one over here with A, B, C, B, A, B, C, D. So let's have an array. We'll make 2 of them. So, okay. So we'll have A, B, C, B, and then A, B, C, D. Okay, so let's take this, move it down here, create a copy, get rid of these because we don't need these. we don't even need the indices really. It doesn't really matter, right? Okay. And we'll make a copy. So one will be like our original word and one will be our copied word. So let's say K, I think K is 2 in this case. So essentially notice every time we move some characters, like let's say we move these 2 characters, we have to do it at least once. Now, as long as this part lines up with the first whatever characters of our word, right? Like as long as this part lines up here, if this part did line up, then these 2 can be whatever we want. So whenever you move characters to the back, you just have to make sure, does the rest of the word line up with the front of the word, right? And once again, if I do another movement, so these don't line up, so I have to do it again. So if I do another movement, this is 2 operations. So we've moved the second half of the word now, right? We've moved all of these. Does this line up? No, it doesn't. So then we have to move 2 more. Like this. Now, these are the only characters we haven't moved now. Does that line up? No, it doesn't. And then we have to move 2 more, and now we would have moved everything, so that's why it's 4, right? So that's why this is 4, and that's why it's 4. So let's go through one that is faster. So let's go through AB, AC, ABA, just for another example. So, okay. And then we're going to really get like exactly what we need to do. So ABAC, A, B, A. And we can get rid of this again and make a copy. Okay. So we have to make one movement once, right? So we're going to take this, put it in the back. Now, does this first part line up with this? If it does, then we're basically done because these can be whatever we want. No, it doesn't. Okay, now we have to take 3 more characters. Put it over here. Now, this is the only thing we haven't moved. Does this line up? Yes, it does. So this can be whatever we want. That's why it's 2 operations. So that's kind of the idea. Let's go back to our original word and let's see what we have to actually do. Because we're not going to be like moving these characters. We're just going to figure out like what we actually need to do. So if we're moving 3 characters at a time, let's say, then we basically need the rest of our word to line up with the start. So if we're moving 3 characters, these 3 will get moved. Then we need this to line up with this. And you can basically do, and this is kind of how you solve the medium problem, you can just basically index. So let's say k equals 3, you would just index at, index 3, and then index 6, and so on. And you'd figure out, does the rest of the word that I have exactly equal the start of the word, the same amount of characters? If it does, then I'm done. And I just figured out how many operations I used, right? So if like this is the first index you access, you would return 1. If it's the second index, you'd return 2, and so on. You can just have a counter there. And so this is enough to solve the medium problem, because in the medium problem, I think these dimensions are like 50. And so this is going to be roughly, so let's say k is really small. The worst case scenario, it's going to be roughly like 50 by 50, because you would basically compare, if k is really small, let's say k is like 1, you'd have to compare 50 different indices of this string, right? Like 50 substrings here to 50 substrings here. So this would be roughly 2,500, which would pass. But in the harder version, this is 10 to the 5th. So this you can't have an n-squared solution. So if you've seen my other videos, essentially you basically need a way to compare 2 strings in O of 1. And if you can do that, if you can compare 2 strings in O of 1, so like let's say I need to compare this thing to this thing in O of 1, if you can do that, then you can get this to pass, right? Because then every single comparison would take O of 1. And you can do this, in fact, using 2 ways. So you can use CAMP, or you could use a rolling hash. And so I think a rolling hash is a little bit more intuitive. If you've seen my other videos, I did a rolling hash, so that's what I'm going to do, rolling hash here. So the idea of a rolling hash is you basically hash your string into a number using both the letters and the indices of the letter. So let's index this letters and kind of show really quickly how this will work. And you can use a pretty easy hash function. So the hash function that you're going to do, and then you can use a prefix sum to maintain like the part of the string. The hash function you're going to have, you want one that, the idea of a hash function is you need it complicated enough to where 2 strings don't hash to the same thing if they're not equal. So like you don't want like this and this, let's say, to hash to the same thing. And if you make your hash function too easy, then that'll happen. But a really common one is you basically just have this. So you have the letter, so ord of the letter, the ASCII value of the letter, times the index, and this is going to be one indexed, so one indexed of the letter, to some odd power. And if you want to make it more complicated, you can use a bigger number. I think I tested it with even like something like 5, it worked. I think a good default one is 131. Or like 31 is a good one. You can look up like what are good rolling hash powers, but it's basically something like this. And you want to keep this number small because let's say this is 10 to the 5th. You can't just do like, 10 to the 5th to the 131 because that's going to be too big, right? So that's not going to work. So you basically need to make this. Actually, I think I have it the other way. Yeah, I do. Okay, so this is actually reverse. So it should be the other way. So it should be 131 to the index. There we go. And this is going to be one index as well. So one index. So for example, like at index 0, it'll be 1. This will be on 131 to the 1, 131 squared, 131 cubed, 131 fourth, so on. But same kind of issue, right? You can't do 131 to the 10 to the 5th. That'll be too big. So the way you can handle that is you can just mod it by 10 to the 9 plus 7. So you can take this whole thing and mod by 10 to the 9 plus 7. And because you're going to be computing these powers, you're going to basically need 131 to the 1, 131 to the 2, 131 to the 3, and so on and so on. You can just pre-compute all the powers of 131 you need before you even do this, save that in an array, and then you can get all these in O of 1. So you just get like 131, then you get 131 squared, 131 cubed, so on, get every single power, pre-compute, save it in an array, and then these things, no matter what index, you can get them in O of 1. So that's kind of the idea, is for a letter at an index, the value will be this. So let's kind of walk through like one letter. So let's say we have this letter C, the value will be ord, or the ASCII value, whatever language you're using, of C, times 131 to the, remember this is one index, so it's not going to be cubed, it's going to be to the 4th. And then you can basically just store all these values in a prefix sum, kind of like a normal prefix sum. All of these characters with an index have a value and you store them in a prefix sum. So if you want like the hash of this, it would just basically be the prefix sum from here to the start, right? You get all these values, you store them in a prefix sum, and then you can get any hash of any subarray you want. Okay, so now the tricky part comes comparing these with the hash. Like once you do this, okay, but what if I want to compare this to this? The problem is the way this is stored in my hash is this C is actually over here, right? So these indices are the same, at least the way they're stored, right? So if I want to compare this, well, my hash for this is going to have these indices, and my hash for this is going to have these indices. So even if the letters are the same, the indices are different, right? So let's just kind of walk through that. So let's say these letters are exactly the same. So let's say this is CABA. So let's say this is like CABA. And I can get the prefix sum really quickly and all that, right? Like if I want to get the prefix sum of this, I can figure that out. Like if I'm over here, I can figure out, okay, like what's the length of this word? And then I can figure out, okay, if the length of this word is 4, let's say, then like I know where it is in here and so on, right? So if this word starts at index 3, then I know it starts here as well. So let's actually change this. Let's say this was CABA, in fact. So this was CABA. Okay, and now if I wanted to compare, actually I don't think I can do it like this. It'll be more like this, but whatever. Let's say these things did match somehow. So yeah, like I said, the problem is my word stored in here would be, or to even make it even easier for the comparison, let's just say these letters are like all A. So let's say these are just all A, and I'm just doing some comparison like this. So the question is now, how do I compare like this section to this section over here, right? The last 4 to the first 4. Because if I move this to the end, let's say, right? Like let's say in my first movement, I took this, let's say k equals 3. I took this, I moved it over here. Or sorry, actually it was this whole bit. There we go. So I moved it over here. Now I need to check, like, is this equal? Obviously it is. But like I said, if I just get the rolling hash here, because the rolling hash is computed with an index and the letter, I'm going to need to use these indices from the old letter. And so if we look at this top thing, this is going to be like, you know, the ASCII value for A times 131 to the 1 plus the ASCII value of A times 131 squared plus the ASCII value of A times 131 cubed plus the ASCII value of A times 131 to the 4th. So that's going to be that one, right? Like this part. But the problem is that this part is actually going to be different, right? It's going to be the ASCII value of A times 131 to the 4th plus the ASCII value of A times 131 to the 5th, and so on, right? So A times 131 to the 6th, and this. And so when I compare them to equality, they're not going to be equal. But what you can do, think about it, right? How would you make these two things equal now? Like, let's say the characters are all the same. How would you make these indices match? Well, it's pretty easy. You just figure out what's the index difference. So here it's 3, 4, 5, 6, and here it's 0, 1, 2, 3. So the index difference is they're off by 3, right? So you could see like the difference is basically where you're starting compared to the 0 index. And so because they're off by 3, because this is basically a level of 131 cubed greater, you can just take this and multiply it, like this whole thing, and multiply it by 131 cubed. And now they'll match perfectly, right? So this will be 131 to the 4th, 131 to the 5th, 131 to the 6th, 131 to the 7th. Then you can easily compare for equality. So that's basically what you do, is you just compute a rolling hash for this whole thing. And then every time you just iterate through the array, starting at the index k. So if you had to move the first k elements, like if you have to move the first 3 elements, then the first location you would compare is index k. You would compare the whole whatever is left to the same length from the start. And then if that doesn't equal, then you remember, we're not actually going to be moving things. So let's actually go back now that I showed how to do the hash. We don't actually have to like do this movement. We can just index and compare. So let's go back over here. So like I said, we can say like, okay, let's compare here to the start. Then if that doesn't work, let's compare here to the start, because now we would have moved 2 chunks. So now we compare this A to this A. And then once we're out of bounds, basically worst case scenario, like I said, is going to be n over k ceiling, because n over k ceiling means we would have moved every single letter. And so if we would have moved every single letter, then we know we could have made the word, right? Because if you can, like I said, if you can change every letter in a word, you can obviously make the other word. And that's kind of the idea there. So yeah, the medium problem, you can just do a substring compare, and the hard problem, you have to know KMP or rolling hash. And I think rolling hash is a little bit, like, I don't want to say it's more intuitive, but that's just one I've done more. So you have to know that, and then you have to realize, like, okay, I just have to compare starting from where I'm at to the same substring in the original word, and then figure out like how many times I moved. So the actual like algorithm part is pretty easy. It's just, do you know how to do one-string comparisons? Okay, and that's basically it. So let's look at the code. So let's maximize, not too much code. So you have a modulo, you have the length of the word, you have the prefix hash, and I made, this is just basically like a prefix sum of your hashes. And then I calculated powers of what you can, like I said, you can use whatever value here you want. You can use 7, you can use 131. I think something like 5 might even pass. Let's see. Oh, looks like it did. Yeah, so you can use whatever you want, but a bigger number isn't going to make it too much slower. So you can go back to 131. Yeah, so you basically just calculate every power of 131 up until the length of the word, because you want to be able to get those in O of 1, right? You want to be able to get these in O of 1, and you also want to get this in O of 1. So calculate and put them in an array, and then you calculate all your prefix hashes for every single word, and you store them in a prefix sum. So like I said, the formula is just the previous prefix hash, if you want to do a prefix sum plus, and then for the current letter, it's the ASCII value of the word times 131 to the index. So powers I is going to be 131 to the index plus 1. And then you mod it to keep it small because it'll get too big. So then you basically loop through all the starting k indices until you're out of bounds, and you get the hash of the current word, right? So whatever you have like for your word left. So let's say we are like over here or something. We will get the hash of this thing, and then we want to get the hash of the word for that many characters as well. So we get the current hash, we get the word hash, and then like I said, to make the word hash equal to the current hash, you also need to multiply it by 131 to whatever power you're currently at to make it the same. So if you're at like index 3 and the other one was index 0, they're 3 powers of 131 off. So you can just multiply it by 131 to the third to make it the same. Then if they're the same, you just return the result, where I just increment it by 1 every time I go to a new index. And finally, if you didn't find anything, then it's just going to be the length of the word over k is ceiling, because that means you've already moved every letter. And so if you moved every letter, then you know it's possible to get the same word. So we can submit it. And I do think KMP runs, I was looking at this earlier, I think KMP runs a bit faster, so this is a bit slower. So because you do have to like pre-compute powers, you have to do a prefix hash. KMP is like a little bit less pre-computing. I think you just pre-compute like one array or something. But I'm not super good at that, so either one of these works. But this is still going to be O of n. You can argue maybe it's like n log n, because like I was said before in a bunch of these videos is the power function. Well, actually no. I think that in this case it will be O of n, because so technically the power function is like logarithmic. But because we're pre-computing and we have to go through every character in the word anyway, I think it'll be like the way we're doing it here, this is going to be linear. So yeah, because we're not using like math.power or anything, which is logarithmic. So if you do a power of like a huge number, that's logarithmic. But this will pre-compute linearly. The prefix hash will pre-compute linearly, and then this thing all these things are computed linearly, and you're going through n over k indices, which is also O of n, if k is like a small number. Yeah, so it's going to be O of n time. And it's going to be O of n space, because we did compute the powers for every single power for the length of the word. We also pre-computed a prefix hash for every single character in the word. So yeah, so O of n space. And yeah, I think I only have one problem to do after this one, which I'll do tomorrow, which is the third one from this contest. So yeah, got most of them done pretty quickly. I think these two contests are definitely kind of a little bit easier than normal. And I do think this problem is roughly the same difficulty, maybe even harder, to be honest, than the one from the bi-weekly contest in the morning. And that problem was 7 points and this one was 6, which I don't really get how that is. So I guess we can look at this acceptance. Yeah, like this was 25. The one in the morning was like 50. So I don't know. Okay, but anyway, that's going to be all for this one. So hopefully you did like this one. And like I said, I'll do the last problem tomorrow. So I'll see you next one. Thanks for watching.